All right, we'll just continue here. We're going to talk about properties and classifications and some measurements together. So when we look at the matter is a physical material of the universe. And so what we want to do is we want to subdivide it. This pretty much contains everything. And so when we categorize matter, one of the first things we can look at is it solid, liquid, gas. We call these the three states of matter, or states of matter. There's a fourth state. Do you know what the fourth state is? Plasma. There is aqueous also. Aqueous would be for a mixture. But just in a broad sense, aqueous would fall into liquid. Plasma. And one way to think about these is if you take a solid and heat it up, you'll melt it, convert it into a liquid. If you take a liquid and heat it up, eventually you'll boil it into a gas. If you take a gas and heat it up, heat is related to what? So if something's hot versus something that's cold, what's the difference between a hot object and a cold object? Yeah, kinetic energy will be higher. And so if you have a very hot gas, then one of the things with a hot gas is you're going to have violent collisions. And the violent collisions can end up knocking electrons off matter. When you knock electrons off matter, that process is called ionization. And so we can ionize things due to violent collisions. And so what plasmas are ionized gases. And they can be partially ionized, like lower energy plasmas, or they can be nearly fully ionized, like high energy plasmas. And so there are lots of examples of plasma, like the sun. The sun is this giant fireball, and that's heavily ionized. And so that's what we call a thermal plasma, or an equilibrium plasma. And then we have these low energy plasmas. And low energy plasmas would be like a neon lamp, or fluorescent lamp. Those would be low energy plasmas. And so we look at the states of matter. One. Okay, the next thing we could look at is it homogeneous or heterogeneous matter? And this is usually just to our naked eye. If you look at things under a microscope or an electron microscope, everything starts to appear heterogeneous. But if it looks homogeneous, then it's uniform in appearance. If it's uniform in appearance, does that mean it's pure? Like a pure substance? No, not necessarily. Homogeneous could be further categorized into two things. It could be pure, or it could be a mixture. So we don't necessarily have to say pure substance. A substance should be pure because substance is kind of strictly defined. How did we define substance before? The substance is either an element or compound. So we'll have element here, or it could be a compound. If we have a compound like water, or an element like hydrogen, one thing about pure substances is the pure substances are going to have fixed composition and fixed properties. So if we're looking at the pure substance water is going to have a fixed composition, 2 hydrogens to every oxygen, and fixed properties. It's going to have a fixed density, fixed freezing point, a fixed boiling point. etc. Whereas mixtures don't have fixed properties. Mixtures, and it can be a homogeneous mixture like air or whatever, mixtures will have variable composition and variable properties. What are the ways we express the composition? So for example, water, there are different ways we can express the composition of water. There are 2 hydrogen atoms for every oxygen atom. We can also express the composition in terms of something called a percent by mass composition. That is a percent by mass. So if we're looking at hydrogen, hydrogen in water is 11%. Oxygen in water is 89% by mass. Oxygen weighs a lot more. And that's going to be fixed. Water is always going to be 11% hydrogen, 89% oxygen. Whereas in a mixture, we can have different composition. And typically, when we express composition in mixture, there are different ways we can express the composition of mixture. Actually, this is going to get a little bit convoluted. I'll need some room here to continue heterogeneous. But let me talk about the ways. So probably one of the most common ways of expressing the composition of mixture is by percent composition, by mass. Sometimes this is written percent M over M. And so, for example, if I'm looking at the percent of A, let's say A percent, typically that's going to equal the mass of A over the total mass times 100%. Percent composition by masses are typically used for things that are fairly concentrated, that have a fairly high percentage composition by mass. But there are mixtures that can have very low concentrations. And if it has a very low concentration, then we might not use percent. We might use something called ppm. Do you know what ppm stands for? Yeah, parts per million. And so this is for very dilute mixtures, where there's very little A. And so when we do A ppm is going to be the mass of A over the total mass. So we'll have the same fraction, except the fraction is very small. Whereas, in the percent, the fraction is usually bigger, getting closer to 1. This fraction is going to be quite small. And since it's quite small, we multiply it not by 100, we multiply it by 1,000,000 ppm. If it's even more dilute, that is, it has an exceedingly small A component, then we might use part per billion or part per trillion. A part per billion, rather than multiplying by 1,000,000, we multiply by billion, and we call it a ppb instead. And so we'll just say etc. So this is a common way of expressing the composition. It's not so common in water because it's fixed. And people don't really think of water as being, 11% hydrogen, 89% oxygen. People usually think of water as being 2 hydrogens and 1 oxygen. But for mixtures, this is more convenient. There are other units that we use. So, for example, we could use molarity. Do you remember the definition for molarity? The symbol is capital M. And molarity is the composition expressed in terms of moles of A per liter of solution. And so this is another way of expressing the composition. So we could have high molarity, low molarity, whatever. Now, water has a fixed composition, 11% hydrogen, 89% oxygen. If we wanted to separate the hydrogen from oxygen, how can we do that? So if we want to separate the hydrogen from the oxygen in water, could we just filter out the oxygen or filter out the hydrogen? Does that work? No. There are two types of separation techniques. The two types are physical separation, like filtration. Give me some other physical separation techniques. Distillation, etc. But we can't do physical separation here. Instead, if I wanted to separate the hydrogen from the oxygen in water, I would have to use a chemical separation technique. And a chemical separation, can you think of an example of a chemical separation technique? Uh-huh.
I'm not sure if I'm getting your name correctly. It's not electric. I just remember it being in the book where there's a.
The electricity thing? Yeah, electrolysis. Electrolysis is very common. So I showed the video at Chem 4 of a 9-volt battery going into salt water and bubbles and gas appearing on the electrodes of the 9-volt battery. That's electrolysis. So electrolysis can be used to break apart the hydrogens and the oxygens to form the elements hydrogen and oxygen. And so an example here is we can take H2O and create H2 plus O2. And we'll need a half O2 to balance it. So we can do that. And then we could separate the mixture here, hydrogens from the oxygen, because that would be a mixture of two elements there. And mixtures can have variable composition. They don't have to have a 2-to-1 ratio. However, for mixtures, we don't use electrolysis to separate. We can separate mixtures easily. So if we had salt water, or we had a mixture of hydrogen and oxygen, what we could use is we could use physical separation techniques to do this. And the physical separation techniques I talked about earlier, like distillation, etc., those would be physical separation. Okay, if it's heterogeneous, then heterogeneous typically means it's not pure. Heterogeneous means it's a mixture. And this mixture can be separated into pure substances by physical separation techniques. Okay, for measurement of matter, SI units, the metric units. Let's talk about that briefly. Density, percent composition. So when we talk about the properties, fixed properties here versus variable properties, there are two types of properties. What are the two types of properties? Physical properties and chemical properties. And depending on the composition of the mixture, the physical properties will vary. And the chemical properties potentially can vary as well. That is like concentrated hydrochloric acid versus dilute hydrochloric acid. There's going to be a big difference between those. For the physical properties, we typically measure those. And so let's take a look at measurement. We're going to be doing a lab on measurement. So I'll talk more about this as we get closer. But we have SI units. And we have SI base units. So for example, length. What is the SI unit of length? Meters. And then we have something called derived units. And so area would be a derived unit. area is you take the base unit and just square it, length times width. So we get meters squared. Or volume, you take length times width times height, we get meters cubed. And so we have the SI base unit meters and then the derived units, area and volume, meters cubed. We also use liters, but liters, those aren't SI units, so we can relate liters to meters cubed and so on. What other? We have density, percent composition, etc. We have time. What's the SI unit of time? Second, etc. We have metric prefixes. You know what the SI unit of mass is? Not grams. It's kilograms, but kilograms is too big. And so the mass is, the SI unit is kilograms, but we usually use grams. And so we need to know some metric prefixes. What metric prefixes should we know? And so we'll start off with big and then go small. What's the biggest metric prefix? Not the biggest literally, but what's the biggest one you should memorize? Okay, nano's on the small end. Mega. Or actually, mega is probably not it now because we have bigger ones. Like if you have a 200 megabyte hard drive, is that very big? Used to be. 200 megabyte hard drive used to cost a lot of money. I remember that. You got probably nowadays tera. What is tera? 1,000? 1,000 gigabytes? Yeah, 1,000 gigabytes. But if you have how many bytes is a terabyte? Is it 10 to the 12? Well, okay, we'll go tera and then what? Giga and then mega. And so a giga is what? 10 to the 9? Yeah. A giga is 10 to the 9, so this has got to be 10 to the 12. And a mega must be 10 to the 6. Mega. And then kilo is going to be 10 to the 3rd. And then centi is a little bit out. Centi is 10 squared, 100. And then we'll go small. We'll go milli. Milli is 10 to the minus 3. And then after milli comes micro, which gets the symbol mu. Micro is 10 to the minus 6. And what's smaller than micro? Nano. Nano is going to be 10 to the minus 9. And then there's going to be one it's an odd one that's inserted here. These are for any base unit or any derived unit. This one is only for length, and that's the angstrom. The angstrom is defined as 10 to the minus 10 meters. You know, what's special about the angstrom? Yeah. The angstrom is most commonly used to measure the diameter of atoms. And so atoms range from about 1 to 6 angstroms in diameter. So this is why this one is important. Okay, after nano comes pico. Pico is 10 to the minus 12. And then after pico comes femto. Femto is 10 to the minus 15. Now, why do we care about femto? We care about femto because of femtoseconds. You know, femtosecond is really fast, right? A lot faster than a picosecond. So do you think you can count to from 1 to a trillion in 1 second? No, but lasers and computers can. And so there's things that can pulse. In 1 second, you can get a trillion pulses. Can you believe that? It's a lot. But it's still too slow. Because some chemical reactions, when the collision happens, it's over in less than a picosecond. And so if you're pulsing at 1 picosecond intervals, you miss it. It was there and then it's gone. Now you have product. And so they have femtosecond lasers which can pulse at 10 to 15 pulses per second, which means that if there's a super fast chemical reaction, you can watch it. And so this is why femtos might be important. That time scale. It's ridiculously short, but some reactions are ridiculously fast. And so they need that. All right, there are other units. We'll go look at these as we go along. But these are the prefixes you should know. All right, problem solving. The bulk of this chapter is problem solving. So there should be one section, problem solving. It's not shown here. We'll talk more about it. Uncertainties in scientific measurements and significant errors. Let's talk about that now. Some things are exact. If they're exact, is there any uncertainty? No. There's no uncertainty. Water freezes at 0 degrees C. That's by definition. It's not a little bit above. It's not a little bit below. It's exactly 0 degrees C. And so there's no uncertainty. But all measurements contain uncertainty. So if it's a definition, there's no uncertainty. But if it's a measurement, there's uncertainty. So when we think about measurements, we think about uncertainty. When we think about uncertainty, we think about errors. We think about precision and accuracy. And so in terms of measurements, we look at errors. There are two types of errors we worry about in measurements. Do you know what the two types of errors are? The two types of errors are systematic error. A systematic error is you're making the same error every single time you take that measurement. And therefore, what you need to do is you need to recalibrate whatever. And so systematic error can be eliminated by calibration. Eliminate by calibration. And so just recalibrate how you're measuring it or calibrate the instrument. And so we should be able to eliminate systematic error. There's another type of error called random error. Random error we cannot eliminate, and this is based on the theory. There's always going to be some uncertainty. It's like, the Heisenberg uncertainty principle? There's always that uncertainty there. And so for random error, we can minimize. But cannot completely eliminate. The way we minimize random error, random errors are these fluctuations. Sometimes it reads a little high, sometimes it reads a little low. Theoretically, we can eliminate it if we take an infinite number of measurements. If we take an infinite number of measurements, and half of those will be high, half of those will be low, and then they'll average. know, roughly will average to the true value. But we minimize it by increasing the number of measurements so we can get a better average. And so the more measurements we take, the better our average will be, and the closer we expect that to be to the true value. And so increasing the number of measurements, and then the other way we can help eliminate it is increasing the precision of the measurements. And so, you know, we could use like a ruler to measure the length, or we could use like a micrometer to measure the length. And so measuring the ruler, you just eyeball it. Using a micrometer, it's a high precision instrument that, you know, is mechanical and can measure very fine graduations, very fine divisions. Okay? And so that way we can minimize. So we try to minimize those. The other thing we consider in measurements is precision and accuracy. So precision just narrows down the uncertainty. So something like 5 grams versus 5.0 grams. Which one has higher precision? Which the 5.0 grams. And the reason is because in sig figs, this is 1 sig fig, this is 2 sig figs. In sig figs, we're allowed 1 uncertain digit. So if the 5 is uncertain, then that means that 5 might be 4.5 to 5.4 grams. 4.5 would round to 5, and 5.4 would round to 5. And so it could be anywhere in this range. So this would be the precision range for this. Whereas this is more precise, because now the uncertain digit is 1/10 of a gram. If the uncertain digit is 1/10 of a gram, then this can vary from 4.95 to 5.04 grams. Both of these would round to 5.0 grams. And so this is a much narrower range, and so it's got tighter precision. This is a much broader range, so it has lower precision. But precision doesn't tell us anything about accuracy. For accuracy, we need to make sure it's well calibrated. So precision tells us the tightness or the reproducibility of the measurements. Accuracy is we got to make sure it's calibrated. So that the instrument is reading accurately, because this balance could be miscalibrated and it's way off. And so you could have a very high precision balance, but if it's improperly calibrated, you're going to get poor results from that. And so these are the things we think about. You think about errors related to systematic errors and random errors, and then think about precision and accuracy. We'll talk more about those as we go along. And sig figs is a measure of precision, not accuracy. All right, there are other concepts that we want to review with time. But what I'm going to do is a lot of this chapter is review from Chem 4 or Intro Chem. And it's still worth reading. But I'm going to jump to the more challenging problems, what they call the integrative and advanced exercises. And so we're going to start off with the tough problem. I recommend doing all the problems. If you're pressed for time, do the problems that I assign. So let's take a look at 67. I don't think I assigned 67. I have to take a look. But we're going to look at all the integrated and advanced problems and see what those are like. So 67, according to the rules on significant figures, the product of the measured quantities, 99.9 meters and 1.008 meters, should be expressed to three significant figures. That makes sense because 99.9 has how many sig figs? 1.008? 4. When you multiply these together, you're going to get 3. Yeah. That's the rules. And so multiplying these together, we get 101 square meters. Square meters being a derived unit from these base units here. This would be area. Yeah, in this case, it would be more appropriate to express the result of 4 significant figures, 100.7 square meters. Explain why. Well, one of the things is, if you look back at the scientific method, where do rules fit in? Did I have rules in there? I had laws. What's the difference between a rule and a law? Yeah, pretty much. You know, rules you can have a lot more exceptions. You know, you can break the rules, but typically we don't break the laws or try not to break the laws. Sometimes the laws need to be modified, but laws are a bit more rigorous than rules. And so we have rules like the solubility rules. Are the solubility rules carved in stone? No. Solubility rules are just some general guidelines. It's not solubility laws. If they were solubility laws, then we treat those a bit differently. And so the sig fig rules, where those come from is they're a simplification of how we handle errors in science. The way we handle errors is by using something called propagation of errors. The propagation of errors is best handled with calculus. Calculus is not required for this course. So we have some simple set of rules, but these simple set of rules don't always work perfectly. And so there are exceptions to the rules. This is one of the exceptions to the rules. Yes, this would be better expressed to this. And the reason is because this. When we look at the propagation of errors, you know, it's the percent error. So what is the percent error associated with this number and the percent error associated with this number? And we should have comparable percent error associated with this. Well, the sig fig rules don't necessarily do that because the percent error here would be a bit higher than the percent errors that we see for these two. And this percent error would be more appropriate. And so the sig fig rules, the basic answer here is they're they're a simplified version of propagation of errors, and therefore they don't always work to give you a good prediction of the actual uncertainty in their final answer, something like that. Let's move on to 68. For a solution containing 6.38% para-dichlorobenzene by mass in benzene, so this is a mixture of para-dichlorobenzene in benzene. The density of the solution as a function of temperature in the temperature range 15 to 65 degrees C is given by the equation. You know what we call this? Is this equation based on theory, or do you think this equation is based on observation? In other words, is it theoretical or empirical? This is empirical. And so what they do is they just look at the curve, you know, and they look at how the density changes as a function of temperature. And they fit it to this equation here. It looks like the density decreases with increasing temperature. That's fine. And so we got lots of these. And then eventually you might think, you know, in theory, what's happening? Why is the density decreasing in this fashion and that kind of stuff? And so we look at that more theoretically or more fundamentally, but we aren't. We could use this equation to predict the temperature, or we could use this equation to predict the density, given the other. And so in this particular problem, at what temperature will the solution have a density of 1.543 grams per milliliter? So we can use this law or this empirical equation, just plug in the density here, 1.543 grams per milliliter, and then solve for T. Does that look like an advanced problem to you? No, this looks like basic algebra, right? Just solve for one unknown. So it seems pretty straightforward. The reason it's advanced is you've probably never seen this equation before, have you? No, neither have I. So that's probably why it's advanced. It's got this empirical equation that came from somewhere. Somebody figured it out. We're just going to use it. We don't have to understand the theory. We can just use that equation to make this simple prediction. So what we try to do is we try to think, this is how I'd solve this, solve for t. If you're pressed for time, you just verify that. So if you have your solutions manual, is that what they did? You look in the solutions guide? Yeah, that's what they did. They just solved for t. It's a pretty straightforward algebra problem. Okay, now things get a bit more difficult. And so most problems are not going to be solved by, like the last example. The last example, we just have an algebraic equation. Let's plug in the variable. Solve for the other. In this particular problem, we use dimensional analysis. And for most of the problems in chemistry, we use dimensional analysis, over 90%. And so number 69, a solution used to chlorinate a home swimming pool contains 7% chlorine by mass. An ideal chlorine level for the pool is 1 part per million, 1 ppm. Think of 1 ppm as being 1 gram of chlorine per million grams of water. If you assume densities of 1.10 grams per milliliter for the chlorine solution and 1.00 grams per milliliter for the swimming pool water, what volume of the chlorine solution in liters is required to produce a chlorine level of 1 ppm in an 18,000 gallon swimming pool? So in the previous problem, it's pretty straightforward what you have to do. In this problem, it's not so straightforward what you have to do. And so in our approach for dimensional analysis, we might not have a clearly defined path that we follow. And so what we'll do is we'll just try to gather as much information as possible. And so typically in a dimensional analysis, we're given something, we have some conversion factors, and we desire something. So there's given and then desire. And so what we'll do is we'll break this down. And so solution used to chlorinate a home swimming pool. So we're going to call this the chlorinating solution. Is 7% chlorine by mass. So 7% chlorine means 7 grams of chlorine, pure chlorine, per 100 grams of chlorinating solution. Chlorinating solution is a mixture. In the chlorinating solution, we have pure chlorine. And so we're going to have 7 grams of pure chlorine and 93 grams of other stuff in this mixture. And so this is it. This is what we call a conversion factor. A conversion factor relates to things. Conversion factors are typically what we call intensive properties. This is an intensive property of this mixture, this chlorinating solution. Intensive, there are 2 types of properties. There's intensive properties and extensive properties. Do you know the difference between an intensive versus an extensive? Intensive property is independent of the amount. So if I had a gallon of chlorinating solution, it's 7% chlorine. If I had 2 gallons, it's still the same, 7% chlorine. No matter how much I have, it doesn't depend on how much. It's always the same. So that's intensive. Extensive properties depend on the amount. So this is an intensive. An ideal chlorine level for the pool is 1 part per million. And so this is going to be pool water, swimming pool water. 1 part per million is 1 gram of pure chlorine in 1 million grams of pool water. So here we converted a percent into its fractional form. A percent means part per hundred. Here we converted ppm into its fractional form. So 1 ppm means 1 part per million parts. 7% means 7 parts per 100 parts. And so the same type of thing here. Yeah. So this is for the pool water. Is this extensive or intensive? So let's say I had an 18,000 gallon swimming pool. 18,000 gallon swimming pool requires 1 ppm chlorine. What if I had a 36,000 gallon swimming pool? Would it require double the ppm? So if I had 36,000 gallon swimming pool, should I do it at 2 ppm chlorine rather than 1 ppm? No, I'm going to do it at 1 ppm. And so this is intensive. It doesn't depend on how big the swimming pool is. We needed to always have this level of 1 ppm chlorine. That's intensive. Okay, if you assume densities of 1.10 grams per milliliter for the chlorine solution, so the chlorinating solution is going to be 1.10 grams per milliliter. So it's grams of what per milliliter of what? And so in Chem 1A, we have to do this. In Chem 4, we don't necessarily have to do this. In Chem 1A, we need to know it's grams of what? This is going to be grams of chlorine or chlorinating solution. This is going to be grams of chlorinating solution. So 1.10 grams of chlorinating solution per milliliter of what? Not pool water. It's going to be milliliters of chlorinating solution. And so this is the density. It's like the density of gold. The density of gold is about 20 grams per milliliter of gold. So 20 grams of gold per milliliter of gold. Well, the density of chlorinating solution is going to be 1.10 grams for every milliliter of chlorinating solution. And 1.00 grams per milliliter for the swimming pool. So if the swimming pool is 1.00, that's close to pure water. Would you drink it? Its density seems to be right on. Would you drink the pool water, assuming it's pure water? No. No, it's probably going to taste pretty bad. And so this is 1.00 grams of pool water per milliliter of pool water. Pure water has a density close to 1. It's actually under 1, so this has some other stuff in there. I definitely would not drink the chlorinating solution. That has a lot of other stuff in there. All right. Is this intensive or extensive? Density. Density intensive or extensive? Intensive, independent of the amount. And then we have 18,000 gallon swimming pool. 18,000 gallon of pool water. Is that intensive or extensive? This is extensive. And so this one definitely depends on the amount. And so if we have a choice, when we start off a problem in dimensional analysis, we like to start off with like an extensive quantity. You know, this is if I change this, it's going to change the volume. Volume is extensive, mass is extensive. So we typically start with these, and these we use as conversion factors here in dimensional analysis. So let's go ahead and start off with the 18,000 gallon of pool water. However, this problem is what we call a two unknown. We have two unknowns here. Because what we're going to do is we're going to start off with an 18,000 gallon swimming pool, and then we're going to add something to that. Do you know what we're going to add? Chlorinating solution. And so to this 18,000 gallons, we're going to add some volume of chlorinating solution. Do you know how much chlorinating solution I'm going to add? I don't know how much chlorinating solution I'm going to add because that's what they're asking. what volume of the chlorine solution in liters is required. So I don't even know how many liters of chlorinating solution I'm going to add because that's what I'm trying to solve. But I need this. I need to know this volume because that's going to depend. The greater the volume, the more chlorinating solution I have to add. Does that make sense? And so this is going to be in liters. And I need to, the units don't match. And so I need to convert from liters to gallons. Do you know the conversion factor for that? 1 gallon is equivalent to 3.785 liters. Now, is this by definition? Or in other words, is this exact? It turns out this is not exact. 3.785, that's to 4 sig figs. Okay, if 3.785 is 4 sig figs, how many sig figs is 1? Yeah, this is going to be infinite here. The reason it's infinite is because of this. It's just by convention. In exactly 1 gallon, there's approximately 3.785 liters. We don't want uncertainty in both. So if we said in approximately 1 gallon, there's approximately 3.785 liters, then that's being somewhat redundant. So what we want to do is we want to fix one as exact and then put all the uncertainty in the other. And so we only have 4 sig figs here in this conversion factor, but that's okay. And so this is going to equal the volume of the pool water. This is the total volume of the pool water. And so this is, when we have 2 unknowns, we need 2 equations. So this is what we'll call equation 1. Equation 1 has 2 unknowns, the volume of the chlorinating solution and the total volume of pool water. So equation 2 is we're going to start off with the quantity of pool water. So we're going to have the total volume of pool water. And this total volume of pool water, we need to chlorinate this to 1 ppm. And so all I'm going to do is I'm going to start off with the volume of pool water in gallons. So this is, the liters cancel and that leaves us with gallons. So this is going to be gallons of pool water. Now, I don't know how I'm going to do this, but what I'm going to do is I'm just going to use dimensional analysis to calculate it. And so the first step in dimensional analysis is trying to get gallons or gallons of pool water to cancel. So I'll put gallons or gallons of pool water. And then I look, do I have a conversion factor that has gallons of pool water? I don't. But I do have a conversion factor that has gallons. And that conversion factor I just used, we'll just go 1 gallon is equivalent to 3.785 liters of 4 sig figs. And so at least I got rid of gallons. And now I have liters of pool water. This might be a dead-end branch. I don't know, but we're just going to try to figure something out. Now what I need to do is I need to get rid of liters or liters of pool water. I'd like to get rid of liters of pool water, but I don't. I have something with milliliters of pool water, but I don't have anything with liters of pool water. So I'm just going to get rid of liters. And since I have something with milliliters, I'll go from liters to milliliters. So I'm going to go 1,000 milliliters. Oops. Actually, per liter. And so the liters here cancel liters. That leaves me with milliliters of pool water. And so I want to go and get rid of milliliters or milliliters of pool water. I do have something with milliliters of pool water. What is that? Yeah, for every 1 milliliter of pool water, I have 1.00 grams of pool water. So in this case, I can cancel out milliliters of pool water. and replace that with grams of pool water. Okay, and then just continue this. Next, I want to get rid of grams or grams of pool water. Preferably grams of pool water. Do I have something that has grams of pool water?
Yeah.
Yeah, what is that?
The 1 gram of chlorine.
Yeah, I have 1 gram of chlorine, pure chlorine, in a mixture containing 1,000,000 grams of pool water. So I can cancel out grams of pool water with grams of pool water. And that leaves me with grams of pure chlorine. And then from grams of pure chlorine, do I have something that gets rid of grams or grams of pure chlorine? Yeah, I have something that gets rid of grams of pure chlorine. So let's use that. What is it? 7 grams of pure chlorine for every 100 grams of chlorine solution. Okay, I'm going to continue it here since I ran out of space. Now, what I want to do is I want to get rid of grams or grams of chlorine solution. Do I have something that gets rid of grams of chlorine solution? Yes, I do. I have 1.10 grams of chlorine solution for every 1 milliliter of chlorine solution. So that gives me milliliters of chlorine solution. The grams of chlorine solution cancel. And I'm very close because this problem is asking for liters of chlorine solution. And so the final step here is going to be converting this from milliliters to liters. And so 1 liter is equivalent to 1,000 milliliters. And so milliliters cancel, and that leaves us with liters of chlorine solution. And so what I'm going to do is I'm going to substitute the total volume of pool water here. And so when I have 2 equations and 2 unknowns, I'm going to do this. I'm going to go 18,000 gallons plus the volume of the chlorinating solution in liters times 1 gallon over 3.785 liters. Okay, that's going to be the total volume of pool water. Then it's going to be multiplying all these out. And so all the units work out. So this is going to be here. I'm going to substitute in here. So this is going to be times 3.785, since the units work out. 3.785. The gallons cancel it. This leaves me with liters on the top. I'll just put the numbers. Times 1,000 divided by 1 million times 100 divided by 7 divided by 1.10 divided by 1,000. And so the gallons end up canceling, and the liters end up canceling, and what we end up with here is liters of solution, chlorinating solution. And so let's go ahead and solve that for that. .785 times 1,000 times 100 divided by 1 million divided by 7 divided by 1.1 divided by 1,000 equals. Okay, that's that. And then what I'm going to do is I'm going to subtract 18,000 from this. Actually, I got to multiply this. So So I can't subtract it. I'm gonna take this and actually I can't quite do it that way, can I? I have to have one more thing in there. Do you see it? Probably. Let me try to simplify this a little bit. We'll probably let this one, volume of the chlorine solution, equal X. And the volume of the pool water will equal Y here. Okay, and then we gotta figure out how we can do this. So this is Y here, the total volume of pool water. So I substituted that here. And then we need to solve for the volume of the chlorinating solution, which is here. And so this is going to be X here. This is going to equal the volume of the chlorinating solution. Which is what I'm solving for here in liters of chlorine solution. And so this equation is going to, let me try to simplify this equation here. The equation is going to look like this. It's going to be 18,000. I'm going to get rid of the unit, plus X times 1 over 3.785. Times this, which I just calculated. Let's see. Which comes out to this whole thing comes out to 4.9156 times 10 to the minus 5. And so this times 4.9156 times 10 to the minus 5 is equal to X. And X is what we're solving for, and that's going to be it. And so now let's solve this for X here. So I'm going to get 4.9156 times 10 minus 5 times 18,000. That gives me 0.88480519. I'm just going to carry extra digits. And then this times this. So this is going to be plus, okay, 4.9156 divided by 3.785. Equals. And so this is going to be 1.2987x is equal to x. Okay, then I'm going to subtract an x from both sides and then subtract this from both sides here. Or did I make a sign error? To double check this. So if I subtract this, I'm going to get 0.2987x is equal to, I have a problem here, negative 0.88480519. So I cannot get a negative number. So I made some kind of sign error here. What did I make the sign error here with? Do you see it? Oh. Well, this is one of the reasons you could have the solution manual. You just look at.
Would be like the new amount of the solution we add to be like ignore. If we ignore, like we add the solution and then there's a new value of the pool, but what if we get rid of that? We just pretend that after we add the value is still 18,000 gallons there.
Yeah, okay, yeah, that's one way of doing it. We can ignore the amount we added and then solve it. That's one way. Let me just redo it. I just had too many numbers probably there, but let me just redo the numbers here and then the math. So this is going to be 18,000 plus X liters of solution that we add. This is the chlorinating solution, and then convert it to gallons. So 1 gallon is equivalent to 3.785 liters. And so we have this. Okay, so this is the total volume of the chlorinating solution. And then we took the gallons and then converted it to liters by multiplying by 3.785 liters per gallon. And then we went from liters to milliliters. So we times it by 1,000 milliliters. And then we went from milliliters of pool water to grams of pool water. It was 1.00. And then from grams of pool water to grams of chlorine. And so grams of chlorine would be 1 over a million. So we went over a million here. And then grams of chlorine to grams of chlorinating solution. And so that was 100 over 7. And then grams of chlorinating solution to milliliters of chlorinating solution, which is 1.10 down here. And then milliliters of chlorinating solution to liters of chlorinating solution, which would have been divided by 1,000 liters. And once we do that, we get liters of chlorinating solution, which is our X here. And so that should be it. Let me just double check this calculation here. And so that was 3.785 times 1,000 times 100 divided by a million divided by 7 divided by 1.1 divided by 1,000. I still get the same. And so 18,000, so I'll go 1 over 3.785 times X times 4.9156 times 10 to the minus 5 is equal to X. 4.9156 times 10 to the minus 5 times 18,000 equals 0.8848. Am I getting the same numbers? 0.519 plus 4.9156 times 10 to the minus 5 divided by 3.785. Oh, here's my mistake. It's 1.2987 times 10 to the minus 5. That's why it was coming out negative here. So this is my mistake. X is equal to X. And so now I'm just going to subtract this from both sides, and then it's going to come out positive. So this is going to be 1 minus this. And so this is going to give me 0.9999959 X. 8840519, and then divide both sides by this. I'm going to invert this. And then multiply this. 0.8840519 equals this. And so finally, I come up with the answer. X is equal to 0.88406 liters of chlorinating solution. All right, there's a way to double check this, but you can already see I've spent quite a bit of time on this particular problem, right? And so this is an advantage of just reading the question and then reading the answer. Then we can see, without making simple errors like this. But there's something else that can help us. If I add 0.8 of a liter, 0.9 of a liter of chlorinating solution to 18,000 gallons, how many gallons is that? And so if I look at this, 0.8 of a liter divided by 3.785 liters, divided by 3.785 liters to gallon, this is equivalent to 0.0. Oh no, not 0.0. This is equivalent to 0.23357 gallons of chlorinating solution. So if I add 0.23357 gallons of chlorinating solution to an 18,000 gallon swimming pool, did that change the volume by much? It barely changed at all. If you add 0.2 of a gallon to this, are you going to worry about it? No. And so this is something that we do a lot in chemistry. What we do is, I could have made this problem a heck of a lot easier. This problem was 2 unknowns because we didn't know how much chlorinating solution we're dumping in there, and we didn't know what the total volume of the pool was. I can make this 2 unknowns into a 1 unknown problem. And the way I make this 2 unknown into 1 unknown problem is like this. I assume that 18,000 gallons plus X gallons of chlorinating solution, actually this we'll call X prime because X was liters, of chlorinating solution is approximately equal to 18,000 gallons. And so, if we're going to add 50 gallons of chlorinating solution to this, then yes, that's going to change the volume significantly. But even if we just add 1 gallon or half a gallon or a quarter gallon, does that change the volume significantly? No. And so what we do is we do this. This is called a simplifying assumption. So what we're going to do is we're I don't know how much chlorinating solution it is, but you don't want to be buying gallons and gallons. When you go to the pool store, do you want to buy, I need 15 gallons of chlorinating solution? No, you just want a little bottle. And you want a little bottle that's highly concentrated so you don't have to add much, right? And so in this simplifying assumption, then this simplifies into a very simple problem. We just start off with 18,000 gallons of pool water. And then we just have one equation, equation 2 that I had up here earlier. So we go from gallons of pool water to liters of pool water. And then from liters of pool water to milliliters of pool water. The milliliters of pool water to grams of pool water. And then from grams of pool water, we go to grams of chlorine. And then from grams of chlorine, we go to grams of chlorinating solution. And then from grams of chlorinating solution, we go to we go to milliliters of chlorinating solution. And then from milliliters of chlorinating solution, we go to liters of chlorinating solution. And so it's just one unknown going through the dimensional analysis problem. And so if we could use the simplifying assumption, then we can make this 2 unknown problem into 1 unknown problem and make it a lot simpler. Does that make sense? So if you had Chem 4, for me, we did this. I went ahead and made the simplifying assumption. I didn't tell you, but I just went ahead and did that. But it's not absolutely correct because the volume did change. The volume changes, and we don't know what the final volume is until we know how much chlorinating solution we added in there. Okay, so what other types of advanced problems do we have? So this was a tough one because this is a two unknown problem, and either you solve it mathematically correctly or you make an assumption. And you have to have some justification for the assumption. In this case, if we went ahead and assumed that the volume, it came out to about the same, liters. It comes out to about 0.88 as well. So it made very little change. So let's look at number 70, since we're going to look at all these problems. Number 70, a standard 1.00 kilogram mass is to be cut from a bar of steel having equilateral triangular cross-section with sides equal to 2.50 inches. The density of the steel is 7.70 grams per cubic centimeter. How many inches long must be the section of bar B? And so, well, first off, a standard 1.0, do you know what the standard is? The gold standard? It's actually not the gold standard, but it's the platinum palladium standard of the kilogram. Have you heard of that? Where's the platinum palladium standard kept? Yeah, in Paris, in some vault, under some kind of blanket of inert gas. But here they're making a cheap one, so this is going to cut this from a bar of steel. Steel's not great because you know what happens to steel? It rusts. And so if steel rusts, then it's going to change the mass. It's going to get heavier as it picks up the oxygen, or it could get lighter as flakes of rust break off. But it's okay. They're probably going to keep it in some inert atmosphere anyway. And so 1.00 kilograms, is that extensive or intensive? Well, mass depends on the amount. And so this is extensive. And so this is probably going to be our given. So we'll probably start a dimensional analysis with this. 1.00 kilograms of iron, Fe. Okay, this equilateral triangle, so it's made out of a bar that's like this. And so this is a big iron bar. They're just going to cut it with a saw somewhere. They need to know how long this is going to be. And the length is how many inches long must this be? So they want the number of inches here. So that's our unknown. The density of the steel is 7.70 grams per. So this is not pure iron. Steel is a mixture of iron plus other elements. And so we'll call it steel. There could be stainless steel. Stainless steel is very corrosion resistant. And so it's probably a stainless steel. There are lots of different formulations of stainless steel, though. Depending. There's 304 stainless steel. There's surgical grade stainless steel. There's magnetic stainless steel like 430, etc. And they all have different elemental compositions, and the compositions are variable. We don't have much time. So the steel has a density of 7.70 grams per cubic centimeter. Is that extensive or intensive? This is intensive. So what we're going to do is we're going to just start off with the 1.00 kilograms and then just try to go from there. 1.00 kilograms. Now, this is a cubic centimeters. This is a derived unit from base unit. And it's going to equal the area times the length. And so if we know what the area is of this triangle, and we know what the length is, then the area times the length is equal to the volume. But the units don't quite work out because this is in centimeters cubed, and the area, this is in inches. And so we've got 2.50 inches here. This is an equilateral triangle. So we could do two things. We can convert the inches to centimeters, or we can convert the cubic inches into cubic centimeters. So what's your preference? Convert the inches into centimeters or convert cubic inches into cubic centimeters? Inches to centimeters. Okay, we'll do that. So we need to know the conversion from inches to centimeters. Everybody should have this conversion memorized. It's 2.54 centimeters is equivalent to 1 inch. How many sig figs in 2.54? You'd think 3, but the reason you have to memorize it is because this is a definition. This is exact, and so it's infinite sig figs. I'll put 3 lines here to define it. And so in exactly 2.54 centimeters, we have exactly 1 inch, or in exactly 1 inch, we have exactly 2.54 centimeters. So we got infinite. And so what we need to do is we need to calculate the area here. And what is the area of an equilateral triangle? The area is going to be 1/2 base times height. Okay. So we're going to have to figure out this height here. So this length is going to be 2.5. This will be half of that, which will be 1.125, or no, 1.25. Right. And then, therefore, this length is going to be what? $1.25? It's going to be off a little bit, but we're out of time. And so this is an advanced problem because we have to look at this. Now, where do we find the formula for these kinds of things? In the appendix. And so we'll look at the appendix next time, tomorrow. So I'll stop here, and we'll continue this problem next time.